Having discussed the concept of what is a state of stress at a point in a generic situation, and that means having discussed the concept of the stress tensor and what is the meaning of each of those components, the sigma xx, tau xy's and all, we are in a position now to discuss about the next concept, which is on torsion. So the topic of this unit is torsion. Now, torsion means in normal English when we twist something. Okay, so just to show you what it actually means, suppose I twist this, I'll come forward so that it will be visible, I think. Yeah. So if I twist this piece of chalk, then it will break. So in fact, towards the end of this unit, we will discuss why it will break the way it breaks. Okay. So just let me do this if it happens. I am just twisting it, I am not bending it. So see, this is pulling. If I pull them apart, it's pulling, which we have already discussed in the axial loading case. One is bending. If I try to bend it, but I am not even doing that. What I am doing is I am twisting it. Okay, twisting it. So let me try to break it till it okay, it broke somewhere. That's fine. So you see this, the shape in which it broke. So that's very important, and we will be discussing in fact the reason why it broke like this. I have earlier made two pieces so that I can show you the actual shape in which they generally break. So see this, I have used two colors so that you can see the shape in which actually they break. Okay, so this is, you are seeing this 45-degree kind of slanting edge in which they break, and we will discuss why it is so. And then to discuss that, we will acquire all the tools, all the concepts to explain the reason why the chalk piece breaks in that way. Okay, anyways, so that means it basically means twisting, but the technical name is torsion. And in engineering application, you generally see this in power transmission. Suppose you have a generator sort of thing, say here it's generates, then you join this by I'll use a different color maybe, and suppose here you connect it through a shaft, right, to the motor maybe at this end. Okay, so this motor drives this maybe in this direction, and then let me erase this much. Yep. So maybe better. So now what we can say is this motor is trying to say, suppose this is grounded, and it is trying to rotate this, drive this. Now in such a case, the load which comes onto this shaft is of twisting. So now the motor is not trying to pull it, it is not even trying to bend it, if we can neglect the gravity in this case. Okay, because of gravity there will be some sagging of the thing which we are neglecting for now. Later on we will come after we discuss bending. But for now, Let's consider that it is just trying to transfer the power by turning it. Okay, so that is a perfect application where we say that a shaft is being twisted or the shaft is under torsion. And as we had discussed in the axial case, I would say that a word pure is also should be added for the discussion which we will have. What it means is our canonical form will be something like this. That means it's a uniform cross section axisymmetric bar. Okay, so all these words are very important. Uniform cross section of certain length, and the cross section must be axisymmetric. We will come to the reason why we have to have this assumption or requirement, but that's the situation. Okay, and then this is being subjected to equal and opposite torques like this. Okay, so which is trying to twist this bar. So that's what we are calling the canonical form of the torsion. So just compare this with the axial loading case where you had this and you just were pulling this with force F. So both sides equal and opposite force was being applied. Now in place of force you are applying equal and opposite torque. So that's the condition. And then this word pure is coming because apart from this no other force is acting on this. That means along with this there could be a situation where you put a force like this maybe on this side also, but we are not considering such cases. Okay, so we will come to such problems in a very later stage. Okay, yep. So that's our basic setup, and then if that is the basic configuration of the force and the geometry, then what sort of stresses do you think will be produced in this body? See, for that you just imagine all this cylindrical body to be a small thickness cylindrical plates sort of. Okay, and then you have high friction between all those separate cylindrical plates. Okay, now if you turn them, what do you think will happen? So each block will try to slip, obviously with friction it will try to slide over the other plate. That means maybe if I initially draw, suppose line like this, suppose I have drawn a line before I have applied the twist on all the different plates. Maybe after all these twists happen, I'll get these lines maybe something like that, right? Maybe, yeah, after that it's not even visible, so they've gone to the other side. Okay, these lines, the yellow lines which was drawn on each of those plates, now they have shifted because of this torque. And so these kind of things, so this is a discrete case which I have drawn. So now you imagine that this thickness becoming smaller and smaller, and it's almost like a continuous line. Okay, so that's now if that's the kind of deformation which we are looking at, then what sort of stresses will be generated. Now you think about the frictional force which we were talking about. So these are the forces, the shear stresses, So if you consider this plate and this plate, what sort of forces or stresses were existing between them? So that is the shearing stress, right? So now when we reduce this thickness to almost 0, that means every cross section is experiencing that shearing stress. So that means it is trying to just slide past the other surfaces which are in contact. Okay. So that means if I pick any of these surfaces, suppose like that, so this surface here is subjected to shear stress tau, and that is true for any surface that I pick. And as in the case of an axial loading, suppose we had this and the normal stress sigma was acting, and we were assuming that this sigma was constant over the full section. It was an assumption, and which was quite a good assumption if you are away from the surfaces where the force are actually acting. And then because it was uniform, so we just sigma times A was your F, right? So this F used to be a sigma times A, but now, or else even if you don't consider sigma to be uniform, what you can do is sigma is a function of maybe whatever the position I am defining by the r vector times dA, and if you integrate over the full area, you will get F. So if you don't want to consider sigma to be uniform, but for the axial loading case which we considered, where the lateral dimensions were much smaller than the longitudinal axial dimension, so sigma was fairly uniform and you had this situation. That is what you always used. But once we come here, the situation is like this. Suppose I go to a particular section somewhere. Now if I go to now on that section a particular point, then if I consider a small area there, say dA, which is at a distance of say rho from the center, then the shear stress which is acting will be parallel to this. So this is the shear stress, and if this is the elemental a small area dA, then what we can write is now tau at that particular location, or so I am using rho, right? Suppose I am using rho, so tau at a particular location rho, it is a function of rho, and then if I multiply with dA, and now that is just the force, but then because it is at a distance of rho, so if I multiply with rho, I will get a moment of that force, and if I sum all these moments over the full area of cross section, I will get the torque. Because everything is in equilibrium, the torque and the internal stresses, so that is how you write the equilibrium equation. The externally applied torque T is equal to the shear stress times the area, it gives you the force, times the moment, times the distance to get the moment, and you integrate it over the area, you will get the torque. Now here there is a very important distinction. So now this torque you must not assume to be uniform, because all the students, they always have this habit of following this axial load method, where we actually assume this sigma to be uniform over the cross section, which is a very good assumption in fact under axial loading, but under torsional loading it is not the case. So that is what I wanted to make it very clear. I want to again emphasize that this tau will be a function of rho, and you cannot assume it to be uniform, and we will in fact derive what will be the function or what will be the distribution of tau over the cross section. But whatever will be the distribution, but this relationship will be valid for equilibrium. Okay. Now, so that's one aspect of the shear stress which exists, but that will also tell us that if I pick a, how would I draw, suppose this is the axis, okay, and from the axis suppose I have let me draw like this, okay. So if I take a portion like this, somewhere, so I'll draw it in a bigger scale so that it will be visible properly. Let me go there. So if now okay, so this is the piece which I wanted to cut from there. Okay, now and then okay, let me draw this to meet at the axis. Okay, so here it would meet on the axis, and so this is my axis line. Okay, now sorry. Now here when we talked about this tau, so if you consider this portion which I have drawn it in a bigger scale there, so this tau is acting on this surface and the surface on the other side, right? So this surface. So if I want to show it here, so basically the tau was acting in this, so tau dA was the force which was acting on this surface basically. Okay, and as soon as it applies here, we know that the same amount of shear stress is applying also on the other side. So if I want to draw the, I'll use a dotted line here like that, and then the same tau is acting on this surface. Okay, so this is that surface. Okay, but along with that we always know, see, otherwise this cannot be in balance. These two shear stresses will try to rotate this block about a line which passes through this surface, right? So that is why, to keep this in balance, we will have equal and opposite torques which will act on these surfaces, which let me give some names to the surfaces so that I can say A, B, C and D. Now E, F, G and H. Okay. So now what I was talking about is this surface A, B, C and D. Okay. So now the tau will be acting here also, and similarly opposite tau will be acting in this direction on the surface E, F, G and H. So that means if I look from this direction, I'll see something like this, So this is, sorry, I'm looking from the top, so I'll see A here, B here, F and E here. So these are the top surfaces, and my shear stresses, which I have shown here, will look something like this. So this is tau, this is tau. So these are these white colors, and these orange ones are in this way. Okay, so that's how your state of stress at any location will look like. So the shear stresses only will be there, but all those things you have to consider. This thing is very easy to visualize, that from the this model, sliding model of plates, but the other one is in a way, they come into picture because these stresses have to be in balance. Another way to realize or visualize the existence of that axial kind of shear stress can be done by, what you can do is you can create a, let me say, draw something like that. You can create a cylinder, but not with solid surface, but using some thin plates like this. You just join these plates and to create a cylinder out of this, like that. Okay. And on this you just attach them by a strip or something. Okay. Now, so they are hinged onto this strip here. Okay, like that, so that you can now twist these things easily. But before twisting them, what you do is you put some stickers, say here you put a sticker, and correspondingly here on this segment, and similarly at 2-3 locations, like that. Now this is the status of the stickers before you put or twist it. But once you twist it, they will slide with respect to each other. Okay, so they will not anymore be like this, but I'll just so they will be like, if earlier it was like that, so this one will maybe it will come like that. Similarly, if this side it is here, so it will come here a bit. They will slide with respect to each other, and that shows you that the existence of this stress. Okay, so you can actually do this experiment at home by getting some these ice cream sticks, okay, and put them on a ring and with pin joints, and then you can twist them to see that, okay, this sliding of the stickers which are closer to each other, they will slide axially. So that will show you that this stress must be developed. Okay, so that is what I wanted to talk about, the state of stress under the pure torsion condition. And in the next segment, what we will see is the deformation. We will define the strain properly in such a conditions, and in fact, to define the strain, we will also see some conditions which exist under such pure torsion case, and then we will go and define the stresses that exist over the cross section. And yeah, so see you in the next segment.